Hi guys, and welcome back to the channel. Today I'm going to be attempting the impossible. I will be explaining quantum computing, and I brought backup to make sure I don't get lost in the nerd sauce. Say hello to my wife. Wife, how was the trip up here?
Treacherous, so make it worth my while.
Perfect.
My job is basically to keep him from using words like eigenvectors and keep us in reality. So explain it to me like I'm ordering coffee. Why is everybody talking about quantum computing?
Okay, coffee. Imagine a classical computer, like your laptop or a phone, and that's a barista. You order 10 coffees, and the barista makes them one by one. Grind, brew, pour, next.
Okay, efficient but linear.
Right, that's how computers think now. They use bits. A bit is like a light switch. It's either on 1 or off 0. Everything you see on the internet now, every photo, every email, is just billions of those bits flickering really, really fast.
Got it. On or off. That's simple, but what makes quantum different?
Well, quantum computers use qubits, and this is where it gets weird. Imagine the light switch again. Instead of being just on or off, imagine it's a dimmer, and it's 30% on or 70% off. And also everything in between all at the same time.
Yeah, you lost me. How can it be two things at once?
Think of a coin. If I place it on the table, it's either heads or tails. That's a classical bit. But if I spin it, while it's spinning, is it heads or tails?
I mean, it's kind of both. It's a blur.
Exactly. That blur is called superposition. While it's spinning, it holds the possibility of being heads and tails simultaneously. A quantum computer works with these spinning coins. Because they can be in multiple states at once, they can do calculations that regular and modern computers physically can't.
Okay, so it's a magic spinning coin. But how does that help us? So why do I care if the computer is spinning?
Great question. Let's use a maze. If a regular computer tries to solve a maze, it tries one path, hits a wall, backs up, and tries another path. And it does this until it eventually solves the maze. But a quantum computer, because of its superposition, can essentially try every path all at the same time.
Okay, so the regular computer takes an hour to find the exit, but the quantum computer finds it in a second?
Less, a millisecond. It collapses all the possibilities into the right answer instantly.
Okay, that's actually terrifyingly fast. What do we use that for? Better graphics for your games?
One can only hope, eventually. But for right now, it's for things like inventing new medicines by simulating molecules or cracking encryption codes that would take a modern supercomputer a million years to break.
So it's not for checking emails, it's for what, solving the world's hardest puzzles?
Exactly. It's not just a faster computer, it's a different type of computer.
Well, as long as it doesn't become Skynet, I'm on board.
Thank you for keeping me grounded.
Always. How about that coffee?
Hi guys, welcome back. I put together a quick PowerPoint just to kind of educate people out there on the possible threats that quantum computing brings. I know there's several videos out there on quantum computing, and I figured having a tech channel and all, I wanted to be one of those videos. The main purpose of this is to explain quantum computing in simple terms, as well as the possible threats it brings. And the main threat is encryption. It can crack encryption and most modern methods for encryption incredibly fast. So hang with me. It'll be a quick PowerPoint and hopefully you learn something. Shor's algorithm can factor large integers exponentially faster than classical algorithms. For RSA, which relies on the difficulty of factoring a large number, it's devastating because the algorithm reduces the time from millions of years on classical computers to seconds or minutes on quantum computers, meaning what would take a million years for a modern computer to crack would take seconds for a quantum computer. Let's talk about AES. Think of AES like a super secure lock. You have a key, 128-bit, 256-bit, so you're going to have a very large key. The algorithm uses that key to mix and transform your data through multiple rounds of substitution and permutation. Without the key, the scrambled data looks like random noise. So once your data is in that lockbox and you look at it, it's going to look like mumbo jumbo. You know, you're not going to be able to tell what it is. Next, let's talk about RSA. This is the identity check. it proves who you are. It's basically the gas station clerk checking your ID to make sure you're of age. RSA is short for the people that invented it. Here are the three OGs now. RSA is one of the ones you don't want to use because it will be very easy for a quantum computer to crack. We also have ECDHE, which stands for Elliptical Curve Diffie-Hellman Exponential. And it's basically the handshake process. What it does is, this is how Joe Schmo over here watching you and Google talk isn't able to get the secret key that you guys decide upon, which keeps your data secure. Imagine you and a friend want to agree on a secret number without anyone else knowing it. Even if someone is listening to your conversation, ECDHE makes this possible. Both sides pick private numbers. They use elliptic curve math to create public values from those private numbers. They exchange these public values openly. Using the received public value and their own private number, each side calculates the same shared secret. So basically, think of it like this. You're talking to the clerk at Google, and they're talking back to you, and you're getting information from them. Joe Schmo over here, in theory, would be able to hear everything you're talking about, see all of your information or bank information, everything, if you're talking about it. What ECDHE does, it's basically the initial handshake, which is some crazy formula that you come up with a number, they come up with a number, which is shared, but you also have your private number, and using some crazy formula, you're able to come up with a secret number that both of you have that actually doesn't go across the wire, that's actually not spoken. So Joe Schmo over here has no idea what that secret is. I know that sounds crazy, but that's how that works. And quantum computing actually can crack that pretty easily as well. Hackers and even some countries are using capture now, decrypt later. Basically, they're capturing your data and they're storing it for when quantum computing becomes more of a thing. And at that time, they'll be able to crack your data and see all of your data. Again, RSA would take millions of years on a classical computer, but just seconds to crack on a quantum computer. Same thing with ECDHE. It's practically impossible on a classic computer, but it would take minutes or less on a quantum computer. The new hero is MLKEM, formerly known as Kyber, Kyber. Instead of curves and prime numbers, it uses multidimensional crystal lattices. Imagine trying to find a specific atom in a grid that has 500 dimensions. It's a mathematical maze that confuses both classical and quantum computers. A lot of companies are actually already using the lattice, such as Google and larger companies like that. They're using the lattice-based encryption on top of the modern-based encryption. That way, one either quantum or modern computer can't crack it, or at least it would be incredibly hard for them to do so. So what can we do? Well, first, you can start using AES 256-bit over 128-bit. Basically, quantum computing will cut the encryption cracking time down by half. So if you're using 256-bit, it's basically the same as 128-bit now. And that is still almost impossible to be cracked. Another thing we can do is enable perfect forward secrecy. And basically, when you're using HTTPS or VPNs, ensure they use ECDHE or similar protocols with ephemeral keys. This won't combat quantum computers from cracking the data, but it will protect the data from people who are storing it now to decrypt it later. Also, you can adopt quantum safe algorithms when available. Again, Kyber, dilithium, and other things that help combat against quantum computing encryption cracking. You can use VPNs with a strong encryption, and that's good to do on any public Wi-Fi as well. And you can keep your software updated. Once quantum computing rolls around and becomes a modern thing, they're most likely going to have something out there that combats it. They're already working on things like lattice-based encryption and things like that. So just keep your software updated so you get the latest and greatest. That's it for today's video. I hope you enjoyed, and if you're watching, don't forget to like and subscribe for more content. Happy New Year's, guys.
Happy New Year's.
Bye.
Do it!